All right, it's September 2nd, 2021, and the central question today is how can we explain projectile motion in terms of horizontal and vertical components? Anybody know what a projectile is? Somebody just throw something across the lab. Don't hit me. Gotta be on camera, guys. Risky. I don't see that. Did I make it? Send it back this way. All right. So projectile. All right, it's going to do this. See? That's the shape that things take here on planet Earth, other planets. All right. If there were no gravity, an object in motion remains in motion and would just go. Right. But there is gravity, and so we got to sort of factor that in. Gravity doesn't act in the horizontal direction. So the key idea here is that in the horizontal direction, there's non-accelerated motion. I did my best to draw these blue horizontal vectors the same size, although I think I should probably do it. But that's the idea there. The horizontal component remains constant velocity, so there's no acceleration. Remember the definition of acceleration, it's the rate of change of velocity. So if the velocity isn't changing, it's not accelerating. And the math is simpler. In the vertical direction, we have acceleration due to gravity. So gravity is a constant accelerator, and it's going to always act on this object, slowing it down until it's stopped right at the peak of its flight, right? So if it still had a vertical component, then it would keep climbing. The fact that gravity has slowed it down to a stop in the vertical direction means that it's at the top of its flight, but then gravity continues to act on it, and that's what sort of brings it back down. The sum of these vectors, we've learned how to add vectors, and so right now they're tail to tail. Okay, and there is a sort of a method to add vectors tail to tail. You basically complete a quadrilateral and connect the diagonal. You know, the diagonal will be also the sum. But we've been learning like draw them head to tail, all right, and then connect the tail of the first to the head of the last. You can see that as the horizontal component gets smaller, right, the sum of these vectors is getting shallower, and that's why eventually it just sort of levels off like this. And so we're using really vector addition here. We're adding the vertical and horizontal components to sort of establish the trajectory of the projectile. Right? So that's why it takes this shape, because the vertical component is changing. Okay, decelerating from launch to the top of its flight, and then accelerating sort of back down, speeding back up. With idealized motion, we have this idea of symmetry of motion. In other words, as fast as it's ever going to move vertically is right when you launch it, right? Because gravity hasn't acted on it yet. And that component of vertical motion will be equal to the down component, like once it's got to the same height again. In other words, it takes, say, 1 second for gravity to slow it down to a stop. Another second later, gravity acting on it, it sped it back up just as fast as it was launched in this direction. So you have the symmetry of motion in the physics professor's mind. Okay, in reality, there are other forces like wind and drag that's going to sort of affect this. And so if there were no air, you know, or other forces, then this is sort of what you would see. But on Earth, it tends to sort of be, the parabola is going to be sort of squashed a little bit in this direction. And it really depends on, you know, other factors too. But we start sort of simply dealing with like one-dimensional motion, and then this is two-dimensional, right? Because we have horizontal and vertical components. And so physics has this sort of method of starting with the simplest case and then adding layers of complexity to deal with sort of the universe, which sometimes is kind of complicated. So try to put that in your own words in your journal. How are we explaining this idea of, you know, launching something and the shape that it takes, so that's a projectile, in terms of both of these components, and make sure you include in your answer sort of this idea. So we have chapter 1, kind of no acceleration in the horizontal. And as we start to deal with more rate of change of velocity, acceleration, that's the sort of physics we're going to apply to the vertical direction. And this is why resolving vectors is so important, right? We talked about how we can mathematically sort of break down a vector into its x and y components. We need to kind of do that because we treat them sort of differently in terms of the physics. We apply the equations of acceleration to the vertical direction, but not to the horizontal direction, because there is no acceleration in that direction. And again, try to just sort of put that in your own words as best as it makes sense to you. Please don't ever just let the notes on the chalkboard stand as your answer. Sometimes students will just sort of get the notes down and it's like, that's the answer, right? But no, you need to kind of go back in and try to I used to have the Cornell notes, summarize it at the end, that's kind of like answering the question at the end. And then if you have any questions, on this side of the lab, there are reflective learning prompt questions. It's like, what questions do I have? What am I confused about? That sort of thing, right? So try to sort of, as you make sense of this, say, well, yeah, that wasn't clear to me, right? And sort of ask the question. Yeah.
What is the horizontal component? If you throw it, doesn't it accelerate?
So yeah, so say like, so kinematics is what we're studying, and that's the study of motion without regard to what's causing the motion. So it's like once it's thrown, right, we've accelerated as much as it's going to accelerate, and then there's no more acceleration. So yeah, that's a good point. Like we have to deliver a force to it, right? And so an object that's at rest, and then we throw it, yeah, we've accelerated it. That's true. But this is kind of like as soon as we've let go, right? So in other words, now it's an object in motion, and the only force that we're really dealing with here is how gravity changes it. Okay. Gravity doesn't act in a horizontal direction. There are forces that do, like wind, and that's why I was mentioning how like really this gravity is kind of be squashed. Newton was sort of hired by the British Navy to work out the trajectories of like cannonballs, and it sort of ships, and he kind of realized like this isn't the actual path that they take. It's a little bit more complicated. There's, again.
And when you add the vectors, what does that mean?
The resultant. So when we sum two vectors, we know that we're getting sort of the resultant, and the shape that the projectile actually takes is this one, right? So we can sort of predict that shape by just looking at sort of the vector sums all the way over. I've drawn a few of them, right? But there's really, this is just a way to sort of think about what's happening in terms of the physics all the way through, right? So if I sort of fill this all the way in again, I always draw the horizontal component, as long as I've initially launched it, because that's not changing. But what's happening to the vertical component, right, is that it's decelerating, and so here it'd be like sort of in between these two. And so if you added those up all the way over, you would establish sort of this shape. That's why eventually at the top there is no more vertical component; it's just going sideways. Okay, and that's why it stops climbing. Right, and then it's just going to speed back up in the down direction. So that's the key idea with that. Do your best to sort of get that down in your journal. That's been the EQ for today.